Okay. So there's a question in the comment section asking if there's any good website to learn about quantum technology. One I would suggest is Qiskit. Qiskit is already it's a platform built by IBM to learn both the concepts of quantum computing as well as get some hands-on projects or slash exercises that you can learn. So of course, there's this platform of Q India. I would request Rishi if he can post some. Thank you. This is the exact. So yes, Rishi has posted this Google form. You can just fill it up if you're interested. It will redirect you towards the Discord channel, and that can be one way of interacting with some people who are all from India and can actually guide you better. But apart from that, my recommendation would be Qiskit. Someone is asking about contribution of data scientists towards quantum technology. Aritra, would you like to take that?
Yeah, so data scientists are in general very required for experimental physics. So there are a lot of data that's coming out from these experiments. And if you try to do it manually, you will miss out a lot of insights from this data. So let's say you're trying to design this qubit. And when you try to characterize that, you see a lot of data that comes out from these systems. So that is how data scientists can help in designing this quantum technologies. On the other side, when you're trying to map an application, something like exactly how data scientists are useful for machine learning type of application, you get this data from different sources. Let's say you're trying to do a quantum algorithm for stock market. So you get this huge stock market data. You cannot put this entire data into the quantum algorithm. So you have to do some kind of data engineering to figure out what is the part that I want to send to the quantum algorithm. So that is again where data scientists are very helpful in understanding how to store this data, how to trim this data basically, and analyze, and finally they work with quantum algorithms. So not one, I guess Achintya mentioned a lot as well. So this is a very interdisciplinary field. So neither data scientists nor experimental physicists nor computer science guys, they're not going to design this entire quantum computer by themselves. So they need to work with many different fields together in a lab, and that's how like you develop quantum technologies.
I would encourage people to just unmute and shoot their questions. I mean, it doesn't have to be even related to quantum technology. Just anything in general would be appreciated. How can one get admission in master's program in India? Is there a specific exam conducted for that purpose? What universities provide masters in quantum computing field? That's a good question, Virat. So yes, as I said, as far as my knowledge is concerned, there's only one university, which is IISc Bangalore. And I'm very sure that it is only one university, that there is no other university that has started this program. And that is in quantum technology, if I'm correct. So it's again very broad, and then you will have various courses in quantum optics and quantum metrology as well. There are various other courses within this program. As far as specific exam is concerned, yes, there's an entrance exam. What is it called? I do not know. It's actually a good question. I should search that. But if you just Google IISc master's program in quantum technology, you will find it for sure. And if I can quickly pull that up, I'll share the link. But definitely there's an entrance exam. Yes.
Right, and like Achintya was saying, right, it's not just that you have to do a master specifically on quantum tech to get into the field. Wherever you are, whatever you want to do, there's always, you can hopefully find ways to tailor your program in such a way. For example, the topic that you choose for your thesis is a very good way to test out the waters in the field and so on. So yeah, good luck.
Yeah, exactly. Like just exactly what Rishi said, that I had like 1 or 2 interns from India. So they were doing their masters in computer science from BITS Goa and BITS Pilani. And so they didn't have a full training. The master's programs were not in quantum technology, but they did their final thesis on quantum algorithms. So it's entirely possible. You don't have to look for a quantum master's, but like as long as you know from these different communities, from Qiskit, Q India, you get to know what the basics of quantum computing, and then you try to tailor your master thesis towards using these things.
There's another question. Would you provide any projects regarding quantum information from Q India?
So Aditra, would you like to take that? Because last time there's a Q intern program. And,
so there are two things. Within Q India, there's a flipped classroom that's managed by Akash Kundu. And so that's more like a weekly or bi-weekly, I guess, gathering where not only students, but even professionals from like people who are already doing their PhD or masters in quantum information. So they come and they discuss different topics. So every week they take up a topic and they discuss them. And that is one way to learn. So there's no certificates involved right now, at least. So this is just getting to know different aspects of quantum information. And then when you have a little bit of confidence, there are, so like there's another thing called Q World. So there are different internships that's going to come out, I guess, in 1 week, the notifications. So in the summer, there is like a 2-month internship that you can do within this Q intern program, where there will be some mentors, might be from industries, might be like PhD students or even professors. And you can work as an intern, you get certificates for that and develop some technology. So you might look out that page, and if there's something related to quantum information specifically, you might join that.
Right, while we're waiting for comments, maybe thanks for the really good talk, Achintya and Aritra.
Thanks.
Wait, so maybe so one thing, I mean, a comment that I would like to add is the way that we at least see, I mean, we are definitely committed to quantum. Our careers have been sort of set in that direction, right? But as a motivation or something that people here could think about is the way that it could happen is like how the history of machine learning was, right? The first machine learning algorithms were probably in the 1950s and so on. But at the time, we didn't have the computing facilities to actualize those algorithms. They were developed and then they were forgotten. And then some 30 years down the line, Google had their data centers and then they could actually do this. And at the time, they solved a problem that was that they thought was not going to be possible to solve computationally, right? And then you see the boom, and now there's a lot of opportunities in data science and so on. So right now with quantum computing, we are sort of at that stage where there's a lot of potential there. Like Achintya and Aritra said, Moore's law is right now stuttering, and the main key point is it's not something like a basic thing you would do, right? So there's a lot of prerequisites that is good to be familiar with to actually work in the field. For example, linear algebra, if you're working in quantum algorithms or quantum information, linear algebra is definite must. And these are courses that people have in their bachelor programs also. So what, like Achintya was saying, what you could do right now is follow up these basic courses like linear algebra and data science and depending on what field you want to go into and so on, and explore a bit, and then I think that's a solid way to think about it.
Sir, I have a question. Could you share any certification or online courses for quantum computing?
Yeah, so online certifications usually, if you want it from some good university, a nice platform would be, of course, edX and Coursera. There are like various courses that are being conducted by various universities. The one that I'm familiar with is from TU Delft, and that is on the basics of quantum hardware. So that is the first certification course. And then the second one goes into quantum architecture. So that's a little bit advanced. So this is the theory side. And that is in that course, there are various professors giving a very short and very brief introduction to various physical implementation of qubits. So how do you actually realize them? So you might have heard of things like superconducting qubits or ion traps, NV centers, so things like that. So this is the hardware side, and maybe even Rishi or Aritra might know there are certain certification courses for quantum information. Do you guys already know certain certifications, Aritra, Rishi?
So I know of a couple of MOOCs and online courses, and like you were saying, these edX courses, they have this possibility of certifications. But I think at least when I've been talking around to people and so on, certifications are maybe not as valuable as being able to convey what the topic is and so on. So even if you don't get the certificate or you can't afford a certificate, definitely follow up on these online courses. And I've posted a link in the chat which has it's really extensive, and this person has a lot of links and a lot of courses that you can follow and so on. And of course, these the flip classrooms that Achintya, Ritra, and all have been organizing within Q India. The main aim is to like make people, make people learn, right? So these are also probably learning circles or opportunities that you could avail and be benefited of.
Yeah, also like specifically for quantum information, there's like it may not be a certificate course, but Arthur Eckert, he's like one of the founders of quantum information. So he offered this course in UK, in Oxford, I guess. And that entire playlist is also available on YouTube. So you can just go take that course by yourself and you would know everything for sure without the certificate, of course. So there's another question on like the quantum machine learning thing. I'll just quickly take that. So machine learning, the core thing that goes on in machine learning is finding correlations and finding patterns in the data. So quantum computer gives you this huge space, this exponential space that I talked about, 2 to the power of n. And you can embed the data inside that space and find more correlations. So that is the basic relation between trying to do machine learning on quantum. So you try to find correlation in a much bigger space, and that will allow you to find better correlations, of course. So that is when you try to use quantum computer for machine learning. And you can also think of it exactly the other way around. People are using a lot of machine learning to design quantum parts of a quantum computer. So for example, in the compiler step of optimizing a quantum circuit, you can use different kind of machine learning algorithms to design better quantum algorithms that would do this operation. So there is like a bidirectional synergy between these two fields that different researchers are like exploring in their research.
Getting back to the question about courses, I would like to actually build upon what Rishi already said, right? So there are, of course, all these different online courses, MOOCs, and etc. But sometimes they expect you to have some preliminary knowledge. So, for example, Rishi has already posted one on in the chat. It expects you to know linear algebra. The one that I was talking about expects you to know some basic physics. So there are some prerequisites, and sometimes if a student joins it, might get a bit too lost or even in some cases demotivated. And then this is why I think these initiatives which we run on of Flipped Classroom actually can be really helpful, because speaking of the Flipped Classroom which I run, which is on quantum hardware, we come down to the most basic level of let's say high school physics and start building right from there in order to understand how a quantum computer physically looks like. So you understand transistors, but you don't understand qubit. If I say transistor, something pops in your head. But if I say qubit, nothing pops in your head. So in order to, make these realizations more visualizing, you need to have discussions rather than just lectures. And that is what we actually aim with our Flipped Classroom initiative, to have more discussions and various other side activities, and using multiple references in order to learn one single concept. So it's actually quite exciting, and I would again highly encourage that first, and then of course you can go for online certifications to put in your resume.
Sir, I have a question.
Yeah.
By when are we going to see the commercial use of quantum computers?
Yeah, so maybe I can again share the very slide which I was talking about. So yeah, I can just quickly do this. So as you can see in this slide itself, right? The development goes from sensing to communication to computing, and likewise, the reason for that is because the engineering and technology is less and less evolved as you go further and further. So to answer your question, first you will see quantum sensors that are commercially available, then some quantum communication tools that are commercially available, and that will again be used by first the governments, the military, and then by banking industry, and then by other corporates. And then finally comes quantum computing, where again, the application will be first seen by, of course, the research institutes and certain pharmaceutical companies for protein folding and understanding or let's say, developing new drugs, certain flight companies. So there are already certain flight companies who are in touch with IBM, Amazon, Google, and these various companies who have quantum computers, small quantum computers as of now, but they are discussing what they can do with the existing number of qubits. So right now we have 50 qubits and people are aiming to have 100 qubits very soon. With 100 qubits, what can you do? So they are trying to formulate certain problems that can be solved, and then slowly you will see that permeating through various other industries, and the commercialization will go on increasing.
So there are a few questions in the chat box.
Yeah. Hi everyone. I would like to... Okay, that's for you, Aritra.
Right, Achintya, I thought you were going to show the meme slide. The application.
Yeah. No. I don't want to demotivate the audience already.
Yeah. So.
No, I'm kidding. But yeah, I mean, of course, this is true with every technology, right? That if you go back in the 60s and tell people that we'll have IoTs and cloud computing, no one is going to believe you, because back then they barely had any transistor. And this is the thing, like in coming 2 decades, you will definitely see some commercial application of quantum computing. That is for sure. As Aritra said, you won't be having it at your home, but you will definitely be seeing it in big companies. So that already is a big win.
Yeah, there's a question for you in the chat, Achintya.
Okay. There was something regarding TU Delft PhD program for Aritra. Maybe we can take that.
I answered that. Like, just ping me on LinkedIn. Any of you otherwise?
Okay. Yeah, you answered it. Okay. Fine.
No
Yeah. So yeah. Can you speak more about the atomic clocks and quantum sensors and compare the numbers in different countries? Well, what kind of numbers do you are you looking for? In terms of sensitivity, or like production? Okay. Well, I do not have numbers for production, but what I can tell you right away is your atomic clocks actually has multiple applications, right? So it's navigation of all sorts. It's timekeeping, precise timekeeping. So for example, in your scientific measurements for your radio astronomy and these kind of things, again, you need very precise time calculations. For defense application, you again need very precise time calculation. So as of now, atomic clocks are used in research collaborations. So for example, these European space agencies, or of course NASA, ISRO, these kind of organizations, they use these atomic clocks. And then of course, military facilities and these kind of organizations. So still the market is very niche. So I don't think there would be any number in terms of production. Coming to quantum sensors, here the market goes a little bit broader, because quantum sensors is a more umbrella term, right? So quantum clocks are only measuring time in a very precise, with a very sharp sensitivity. Quantum sensors in general can measure, like it can be of various types. So force sensing, acceleration sensing, field sensing, uh, photon sensing, all of these. And there the application goes a bit broader. But then again, there are most quantum sensors currently only in the domain of academics. So as I was talking about, these large hadron colliders, particle accelerators, even for space applications. So some people are planning of sending superconducting cavities into satellites, and then scaling them up, or using some kind of technology such that they can detect dark matter or some background radiation with these kind of sensors. So even there, the technology currently is niche, but then it is growing more towards other industries. For example, geospatial imaging, or defense applications. As of now, and then again, I think at this very start of this talk, Rishi and I were talking about these magnetic sensors, right? So we can quantum sensors also have applications in biomedical imaging, in terms of detecting magnetic waves or electric fields coming out of your brain or even from heart, and then they can be used again for imaging the brain or heart, and these various medical. It's like a non-invasive tool. So yeah, I would say that the market is expanding, but in terms of numbers, I cannot provide anything. I hope that answers your question. If not, do let me know. Darshil is asking, I would like to pursue masters in quantum technology. Can you guide people for it? Oh, absolutely. We would love to do that. I mean, great. So Rishi has already sent our LinkedIn profile. Rishi is on point. Thanks a lot. If you already have some questions, you can send us a LinkedIn request. We can chat on LinkedIn as well. And then, of course, there's this platform of Q India, where we can again have a more broader discussion with more broad range of people. Because what kind of masters you want to pursue, it depends on that. But of course, we would be more than happy to have a further chat about this. Could you suggest any book or reading material for an absolute beginner with only mathematical knowledge? I'm guessing you're looking for something in the theory. So yeah, Aritra, it is this
Nielsen and Chang.
Nielsen Chuang. Yeah, exactly. So yeah, exactly. So maybe you can.
That is like the Bible of quantum computing.
Absolutely.
That's what known, but also very few people has read it end to end. Definitely not me, probably not my professors as well. So it's good to start, like keep handy when you need to, let's say, check out a derivation or something, but it's not like the best resource to start off with. I would suggest check out popular science quantum videos on YouTube, because videos are much easier to get started with. Then go into like specific introductory lectures again on YouTube, and then go for like this books and papers. So this is still a field in development. So let's say Nielsen and Chung doesn't even have the most important algorithm that is used now, variation algorithms, and it's because this field is developing so fast that there's no one standard textbook for it. Best is to like keep updated with the latest resources on videos and articles, but research articles would be definitely much more involved. So yeah, keep trying out videos on YouTube. That's the best thing. And of course, like another point is, if it's not for quantum information, I'm assuming it is, but every different thing of this quantum stack, like hardware and information and programming, each requires a different resources to learn from. So there's no one answer to it. So the best thing is just get in touch with either one of us or like the Q India Discord server, and we can discuss and help you out with what is the best resource to learn that specific thing.
Just to add, those who are in the electronics background and would like to see it from a more electronics perspective, I've already shared a link, which is basically like a primer in quantum computing for RF engineers. So that is also a good read. There was, I think, one more question. Is quantum computing hardware used for general purpose computing, or are they designed specific to applications? Yeah, this would be again in line with what Aritra talked about in his talk. So the answer is no, it is not. As of now, not for general purpose computing. As of now, in future, what happens, we do not know. So for now, the application is very niche, and that is to dump only that those type of problems. So basically to formulate such problems that a quantum computer can solve, give that to a quantum processor, get a quantum output, make it classical, and then use it for your other type of calculation. So to give you an example of that, one such application would be these traveling salesman problem, right? I think people from computer IT background might have heard of this. So let's say you're an aircraft company, you're like Lufthansa, Boeing, or Air India, or any of these, and you have to do all these logistics of different flights going from one place to the other, and you want to minimize that because of course you want to save fuel. So to minimize that, the problem as it scales in space, time, and number of flights, it goes way beyond normal computing capabilities. And for that, there are different models, maybe Aritra knows, to formulate these kind of traveling salesman problem, or let's call it flight logistics, to formulate them in such a way that a quantum computer will give you an optimized solution. So it will tell you that for these initial parameters, this is the kind of layout you should go with, or these are the kind of output that you can have. And then you will translate it into your classical computing terms, the variables that you want, and then you will use it for your further processing.
Just a little bit on that. So there are basically three classes of problems that you can think of. Some things which are very easy for your computer, and these things will also be easy for a quantum computer, right? So there are things which are both easy for classical and quantum computer. The middle part, the medium difficulty, are the ones which are difficult on classical computer, easy for quantum computer. And then there are like super hard things which are both hard for classical and quantum computer. So of course, in principle, so if you look at this structure of these three problems, if you have a quantum computer, you don't need a classical computer. So this is in the theory world, that if you have a big enough quantum computer, you can do everything on it, from playing games to everything. But the point is, we don't have it, and it's a very scarce resource. So we want to really use it to the best like frugality as possible. So we don't run the things which are easy already on a classical computer on a quantum computer. So that remains here. Again, the things which are very hard, we don't run it on. We can as well as use classical computers. Why use a quantum computer for it? Anyway, we are targeting an approximation of the answer. So this middle sweet spot is what we try to identify, and that is the main research in quantum algorithm, trying to identify what problems are good specifically for quantum computer and bad for classical computers, and try to run those on a quantum algorithm and quantum computer.
The questions are actually really good, I must say. I'm really happy that so many people are actually interacting and showing so much interest in quantum technology. What are some of the unsolvable real-world problems that quantum computing cannot imagine to solve? Wow, Aritra, that's for you.
It's kind of part of my PhD thesis, actually.
Oh, okay. So let's book 1 hour session then.
So there are certain problems which are both difficult for normal computers and quantum computers. But even for those problems, quantum computers are slightly better than classical computers. So you can use that slightly things for getting an advantage. So there's this unsolvable term it can be interpreted differently. Either you think of unsolvable as you can never find the best answer without some kind of a brute force, or you can still find an approximation using some smart heuristics. For example, the traveling salesman example that Achintya gave is pretty hard, even for a quantum computer, but you can still get a little bit better answers on quantum computers than on classical computers. So as long as we can formulate some problem as a as an algorithm in general, it is no longer unsolvable. It is either you get an approximation or you solve it perfectly. So that is like the beauty of quantum, like computation in general. If you can formulate something, you can solve it.
That's a really nice way of putting it. If you can formulate it, you can solve it.
That's the church-Turing thesis, my friend.
Yeah. Aritra?
At least for the next, like, it's very hard to predict, and it's like I'm risking being wrong over here, and would love to be wrong, but probably in the next 50 years we would not have a quantum laptop or a PC. But as I said, I would love to be wrong. Right now, quantum computers are kind of mainframes, like will be, at least in the next 5 to 10 years, they will be on the cloud as a supercomputer kind of thing. So it will what's called as a platform as a service. So you can buy compute hours on that quantum computer, send in your problems, like send in your like stream of data and algorithm is going to run that calculation and give you back the result. So this is the current, at least how we understand it clearly right now as a research perspective. This is how the pipeline of a quantum computation would work for at least a couple of decades.
And looking at the hardware side of the things, that actually explains why this is a limitation, right? So in principle, you can have as many qubits as you like, but when you try to realize these qubits, it turns out that there are lots of engineering challenges which prevents this from happening. Mostly material challenges, what type of material to use, what material properties can be optimized. There's a whole branch of material engineering or quantum engineering that just does these, right? Like band gap engineering and whatnot. And then there are RF challenges, like reducing the noise or improving signal to noise ratio. Challenges in terms of the dissipation mechanism. So basically all the unwanted things that are affecting your system. Heat, I mean, if it affects your normal computer, for quantum computer, you can simply imagine, right? So these are the challenges that are currently preventing this scalability. And one of the real challenge actually lies in here, and that is why you see that there are so many different architectures. I mean, one would argue that okay, one architecture is enough, right? Why do we have 5 or 6? Because we don't know what can actually go to thousands of qubits, whether it's superconducting or ion trap, and then we basically experiment with all of these and show some promising results, and then people keep pouring money into all of these. So that is where actually the limitation lies. But theoretically, as Aritra sees it, yeah, sky is the limit. Yeah. Comment by Aritra is lit. Yeah, so yeah, we have this another question: which industries will benefit the most from the use of quantum technology? I think even Aritra can add a few, but I think immediately it would be quantum technology, you say, right? So it's not just computing, it's computing, communication, sensing, all of these. As always it is. The military, right? The defense always benefits on all aspect, communication and sensing the most. Computing, I do not know. But apart from that, pharmaceutical companies. So Aritra also touched upon it. Basically, whenever you're whenever you're developing a drug, you need to know how proteins fold. And only when you understand the protein folding can you actually synthesize a molecule that that can be used for a certain what do you say, medical application. And these protein foldings cannot be simulated with a normal computer because it's a quantum system, right? Because it's a molecule. Finding the ground state becomes really difficult, and then again you use a quantum computer for that. So pharmaceutical companies can benefit by finding better drugs using these techniques. In addition to that, then there's of course material companies who can find better material properties by finding which parameters can be optimized in order to gain what do you say, quality, because these days simulating materials is beyond the scope of normal computers. And then of course logistics, so these flight companies, but then again it depends on how easy or difficult the problem is. I would say these are the current areas, and then maybe Aritra, you would like to add some?
I kind of completely agree with you. Material science will probably see the earliest application of quantum computers. But there's another thing called quantum simulators that a few companies are working on. So that's like a special purpose computer, similar to an ASIC stuff, where you design a specific circuit to optimize something specifically. Since like general purpose quantum computers or programmable computers are a little bit more difficult to make. So these companies are mostly working mostly with this molecular simulations, and that is the domain. And then you can choose what molecule you are simulating. Bigger molecules are obviously difficult to simulate. So for example, drug discovery requires much bigger molecules. But smaller molecules, something like batteries, like optimizing the reactions that are going on in batteries would help in designing better batteries and energy efficiency and those kind of things.
Also, to maybe just add a comment while we're waiting for questions, it's that one of the good things about quantum computing and the field is that it's very new, right? So there are the algorithms that we talk about, these Shor's algorithms, these Grover's algorithms. If you compare that to the number of algorithms that exist in classical computing, in decades of research that's gone into classical information processing, it's very finite. It's very less, because again, the way that you think about these algorithms and try to develop these methods to actually solve problems or map actual real life problems onto techniques that are implementable on a quantum computer are completely different. It's a complete paradigm shift, right? So there's a lot of potential there's a lot of ground to cover, and that's another reason why the field is, at least to me, very exciting and interesting.
Yeah, like from my personal experience, when I started my master's thesis research, I wanted to do something using like genomics data and quantum algorithms. But at that time, I couldn't find any literature review. There were hardly one or two people before me who tried out. So the first notion for running on a quantum computer. That's why people didn't work on it. Or maybe when people worked and they found out that's not good, and then they left it. What I eventually found out over my research is, no, that's not the thing. It's just that not many people really thought of looking at genomics from quantum algorithms. And this happens a lot. Even the other things that I worked on, it's very easy to find topics where nobody has even looked at right now, and try to see whether you get a quantum benefit or not. So that's something really good. It's like the field is much new, what's called as like low-hanging fruits for research. I'll take the next one as well. So role of quantum communication for interplanetary communication infrastructure. So right now there are a couple of, maybe one or two satellites which have demonstrated quantum data communication capabilities. The primary objective of that is to make data more secure. Okay, so you want to establish the security between the data at these two places using this quantum communication protocols and cryptographic protocols. In the interplanetary communication structure, let's say you have a base in Mars and you want to communicate using a quantum channel. You would want to do that if what you're transferring is a very secure data. Otherwise, why take the trouble of having this quantum communication infrastructure over it? In fact, in most of the planetary communication, the data rate and the overheads are so high that you just want to know whether those astronauts are okay or not. You don't even like add a layer of cryptography, a layer of encryption on it. You just send the data over, in fact, multiple times so that at least one of them reaches Earth and you know that, okay, they are good. So it's not everything is about security when it comes to interplanetary communication. What's most important is the signal strength and getting the signal back on Earth on time. So probably not the first application of quantum communication. It will mostly be used for like secure transactions and like sending passwords over the internet or for banking transactions.
Actually, yes. What Aritra says about the infrastructure and all the logistics cost, that actually is currently the most biggest challenge. And yes, quantum communication predominantly is used for security purposes, but just to brainstorm and think a little bit beyond, because I can maybe see where this question is coming from. If I take the liberty of replacing the word interplanetary to intergalactic, then maybe it can have some applications, because there's this famous ERP paradox, right? That if you have entangled qubits that are light years apart, even then the communication will be extremely, the communication will be at the speed faster than the speed of light, which is what Einstein was basically opposing. So maybe this could be used, because if it is galaxies apart, the communication will take years, let's say, if you go with normal conventional communication. But again, that's like civilization 2 or 3 level talks, but it's good to brainstorm.
Hopefully we'll have a quantum computer before that, but maybe
yes.
There's something else in quantum called as super dense coding. So you can send 1 qubit to transmit 2 bits of data. So that can be, again, very well applied for this interplanetary communication. So when you have a good link with the astronaut somewhere, you send 1 qubit. And then when you do not have a good link, you use that qubit to send 2 bits of information across these 2 places. So that can also be that can also be useful for this interplanetary weak link kind of communication channel.
I think since we have already crossed the limit, shall we start concluding? Aritra, do you have any final comments?
Not much. I hope to see most of you in the Q India platform, because of course, like 1 hour or 2 hours is not enough to explain everything and all the questions that you have. So it will be good to interact in any platform. It need not be Q India. It can be on LinkedIn, and then just like a longer term communication channel that we can know more about, and we can guide you through this process of quantum education.
Totally, and it's been a really good experience to see so many people interested in the field and interested in hearing about quantum and so on. And special shout out to Yash, who invited us from the college, right? Thanks Yash. And Achintya, I think he's maybe not here, but thank you everyone for organizing this talk.
So before concluding, I'll request everyone to switch on their videos so that we can take a quick snapshot of all participants.
Yes, that'd be really nice. Yes. Where is Achintya? Right. Hey Tamal, how's it going?
Is he back?
No, just a second. Let me text you. Oh yeah, there he is. Nice.
Yes, I'm there.
Yeah, we were taking photos, and then you.
Okay, cool.
Right at that time, so it's like.
Absolutely.
Uh, hey, Niranjan.
Okay, so the
Done.
screenshots are done. Good evening, everyone. This is Yash Amin, the event manager of IEEE TCT student chapter, and it is a great honor to propose the vote of thanks on behalf of IEEE TCT committee to all those who have helped us in making this event such a success. First of all, I'd like to propose a hearty vote of thanks to our speakers, Arita and Achintya from Q India, for making an intimidating subject like quantum technology so easy to understand, and for covering various topics starting from introducing us to quantum computing, algorithms, applications, and sharing information on quantum hardware and opportunities that for those who are interested in this field. As no event can become successful with a single person, I would like to extend my huge thanks to all the participants who have turned up in such great numbers. Thank you so much for making this event a success and for your active participation. I appreciate your patient listening. Furthermore, I would like to express my profound gratitude to our principal, Dr. B.K. Mishra sir, for believing in us and giving us the opportunity to organize this workshop. I also wish to express my gratitude to our IEEE branch counselor, Dr. Lochan Jolly ma'am, and our beloved HOD, Dr. Paya Saha ma'am, for providing us with encouragement and support. I am also very grateful to Mr. Deepak Shetty sir and Mrs. Aradhna Manika ma'am for their constant guidance and support and encouragement. Lastly, I express my vote of thanks to the core team who worked day and night for making this event such a huge success. Once again, thank you all for your cordial cooperation. Thank you, everyone.